Hi, my name is Harold Ng, and welcome to this tutorial where we will turn a simple single-server database service into a distributed version using OmniPaxos. As shown here to the right, we will use OmniPaxos to replicate the database safely across multiple servers through its log API, and without having to implement consensus ourselves. So we can first take a look at how our single-server setup works. We can start the system by using Docker Compose, and then on this left-sided terminal, I will attach myself to the client. And in this way, we can, from this terminal, perform operations such as put and get, and also delete, right? And now, since it's a single server setup, it means that if I kill this container that is running the server on the right here, then we can see that it says it's disconnected. And from the client side, we will not be able to do any operation. So this is what we will fix with OmniPaxos. We will now add the changes to make our system get replicated by OmniPaxos. And we begin by going into the cargo file to add the OmniPaxos dependencies. Here we will use the Git version, but normally you can use the version on crates. And then we will use two features, the serializer feature to derive the serializer and deserializers for our OmniPaxos messages, and also the macros features to derive an implementation required by OmniPaxos. And we will also use the OmniPaxos storage crates to get a storage implementation to store the log and state of OmniPaxos. So now we can go and define the struct, the OmniPaxos struct that we will interact with. So I will import OmniPaxos and also the memory storage, which will store the state and the log of OmniPaxos in memory. And now we can define our OmniPaxos struct as a type alias in Rust called OmniPaxos KV, which is the OmniPaxos struct, which has two generic arguments. The first one is the type of the log entries, which in this case is KV command. And then the second one is the storage. So here we want to use a memory storage that stores KV command. So now to see if this compiles, we will just instantiate it with a to-do. And you can see that the compiler will complain about that the KV commands that we want to store in the log does not implement this entry trait required by OmniPaxos. So to solve this, we will go to the KV file where the KV command is defined and use the macro that I imported before. So here in the derived, we simply use the derive entry. And if we now recompile, we can see that the error is gone and we only have a few warnings related to the to-do, which we will ignore for now. So now we can go to the server and add OmniPaxos as a field in the server and see how we interact with it. So we will create a new field called OmniPaxos, which is the OmniPaxos KV that we defined. And we will also add a new field called last decided index, which will help the server to keep track of how far in the OmniPaxos log it has read. So now when we process a client request, we cannot just apply it directly to our database, because if we do that and servers get client requests in different order, they will diverge and become inconsistent. So instead, we will first try to append it to our OmniPaxos log, which we simply do by calling append on OmniPaxos. And what we have to do instead is that we create a new function called handle decided entries, which will check if the OmniPaxos log has decided any new entries. And if that is the case, we will apply the changes to our database. So the idea is that the OmniPaxos log will provide a single order replicated on all servers, which they all follow in order to be consistent, right? So we will first check if OmniPaxos has decided something new by calling self.omnipaxos.get decided index. So if this new decided index is greater than what we last saw, then we will read all these new entries, right? So do this by using the function read decided suffix, which returns all the decided entries from a given point in the log. So here we do the last decided index. Okay, so now what we want to do is to, for each of these entries here, apply them to our database. So we will create a new function called update database, which simply takes these decided entries as an argument. this, and then we simply iterate through each of these entries, 4 entry decided entries, and then apply the change to our database, right? And here we need to just match on the log entry so that it's decided, and then do self.database.handle command. Well, so this was the same function call we used to do when we received a client request, but now we do it only when the entry relay is decided in OmniPaxos, which means that all servers will see the same command in the same order here. Okay, so now we go back here and simply call self.updateDatabase of decided entries. And what we need to, what we can also do is to reply to clients. So we can do a message, which is a API response to the client. And here we need to actually define a new type of response. So we can do like just a decided to let the client know about how far in the log we have decided. And then here we can just do the new decided index. Actually, before here, we need to make sure that we update our last decided index to this new decided index. Okay, and then we simply send this to the client, right? So that we do through the network, where the client has the ID 0 for us, and we just call message and await. Okay, and at this point here, we can also add some printouts just for the demo so that we see how our log looks like after every decided entry, like after we have handled every decided entries. So here we can again use self.omnipaxos, read decided suffix, and here we can just read it from the 0 to look at the whole log. Okay, good. So at this point, we have changed how we handle a request. So we will first append it to OmniPaxos and then continuously check for committed entries in OmniPaxos and apply them to our database. But in order for entries to actually get decided in OmniPaxos, we have to do the messaging between the servers so that they can agree on the ordering, right, to get stuff decided. So we will now implement this messaging between servers. So we go to network, and here we now need to add a new type of message for the OmniPaxos messages. So we start by importing the OmniPaxos messages. And since these names clash, the message, we will call these OmniPaxos messages OP message. So then we simply add a new variant of messages, which we can call OmniPaxos message, which are a OP message that carries the KV command type. Okay, so now if we go back to the server, we will add a new function which sends outgoing messages. So what this function needs to do is that it needs to periodically go to the OmniPaxos struct and fetch the outgoing messages and then send them out to the correct or intended receiver. So we begin by going into OmniPaxos and then get the outgoing messages by this outgoing messages call, which returns a vector of messages. And then, so then we can iterate through each message and then check who is the receiver for the message, which returns a node ID, which is just a U64. And this we have to send to the correct server. So the idea here is that every server has a unique node ID, and we have to send it to this specific server. And in our case, we have mapped each server or each node ID to the socket of the server. So here we simply do receiver and then the actual message. And here we need to wrap it in the OmniPaxos message that we just defined. So so here we fetch the outgoing messages and send them to the intended receiver. And we, as a user, we don't have to worry about what happens if messages get dropped or delayed. If there is a need for resending messages, OmniPaxos will generate them and we will get them through this function call, and then we just send them as usual, right? So the important is to simply call this function periodically. So now we also have to add how to handle the message. So if we get an OmniPaxos message from our network here, then we simply call OmniPaxos handle incoming of message. So yeah, that's it. That's the messaging part. So we need to periodically go and fetch the messages and then feed them into our OmniPaxos. So now we will change our run function so that we actually not just wait for messages, but also send out outgoing messages, right? So here we'll try to send outgoing messages every millisecond. And another thing we need to do periodically is to check for the decided entries and apply them to our database. And one more thing we need to add here is that we need another timer, which we can use for every 10 milliseconds instead. And this is to tick the internal clock of OmniPaxos. So the purpose of that is that this internal clock will help us to detect if a leader has failed or detect the need for resending messages. And so after a certain number of ticks, we will do the actions required. So here we simply call self.onlypaxos.tick. Okay, so at this point, we have implemented all changes required for the server. The only part remaining now is to go back to our main file and actually build OmniPaxos. So for this, we need to create two configurations, which is one, the server config, which is unique for every server. So here, the important fields are PID, which is the unique ID for every server. And here we use the environment variable from Docker. And the second one is the election tick timeout. So this is how many calls to tick before we consider that the leader has failed if we don't get any messages from the leader. So here we set it to 5, and we set the periodic timer, the tick timer, to 10 milliseconds, which essentially means that we use a election timeout of 50 milliseconds. And then the rest we can just set to default. And the second config we need to put is the cluster config, which should be the same for all servers in the cluster. So the cluster should have a unique ID, which here we will just use 1. And then we need to define the nodes that we actually have in the system. And this, again, we will just use the environment variable from Docker. But essentially here we need to put a vector of the PIDs. So if we have 3 servers with the PID 1, 2, 3, we would do something like this, right? And then again, the rest we can just leave as default. So now we only need to create a OmniPaxos config, which is a wrapper for these two. So we can do server config, cluster config, and then we can build our OmniPaxos using this op config, this build function where we need to provide a memory storage, and here we just initialize it with the default. So then we can up here. So here we will now just use OmniPaxos, and then the last decided index will be initialized to 0. So we have now added all the changes required. So the changes were mainly in the server, where we had to implement how to interact with the log, and also how to do the messaging between the servers, right? Now let's try out our system that is being replicated on OmniPaxos. We can start it by using Docker Compose. And in this top terminal, I will attach to the client, where we can then propose commands to the system. And then here at the bottom, I will attach to one of the servers so we can see what's going on with the OmniPaxos log. So here at the top now, I can do puts, different keys, and also deletes and do gets, right? And we see that all modifications, the puts and the deletes, they are all added to the OmniPaxos log. So now in the top right terminal here, let's try to kill server S1. And we can see that it says that it's disconnected, but we will still be able to do gets and puts as usual, right? Because we still have a majority of servers, which are S2 and S3 in this case, that are still running, right? But now let's say that S2, for example, disconnects from server S3, let's say. So we can simulate it by Docker pause here. And we can see that when we do Docker pause, then the servers obviously cannot communicate because S2 is paused. Then if we try to do a get A, that gets sent to S2, nothing happens. But this still works if we send it to server S3. But if we try to do a put, then we will see that nothing happens. right? And even if we send it to server S3, nothing happens because the servers cannot communicate. So the operations, they cannot be replicated on a majority, which prevents it from being committed and applied to the database, right? So what's also interesting is that if we now, just to make sure that it really gets a put at server S2, is that essentially now we have 3 values that are pending or concurrent, and some of them are received from one server and some of them at the other, right? So this really requires OmniPaxos to make sure that the commands are put into the log in the same order at all servers in order for the servers to not diverge and instead remain consistent, right? So if we now try to unpause S2, we can see that all 3 commands, they get put into the log and in one single order at all servers, right? So first of all, we see that all 3 commands are put into the log. We see that this 12 was here, and the 13 was ordered before, and 14 was ordered last, right? So now if we try to do a get A from server S2, we see that it's 14, and if we do it from server S3, we also see that it's 14, right? So it's consistent here. So at this point, we have a replicated system where every change to the database is appended to the OmniPaxos log. This is not very practical because our log will grow infinitely large over time. So what we can do is to use the snapshotting feature in OmniPaxos, which can allow users to define how to squash multiple log entries into one entry that summarizes the application state. So in our case here, for example, let's say we want to snapshot 5 entries, then we would take the latest value per key for those 5 entries. So in this case, we would only keep A as the value 3 and C as the value 10. So we will now change our code to use the snapshotting feature in OmniPaxos. So we begin by going into the KV file and define the data structure that represents our snapshot. So the idea here is that we will have a field called snapshotted, which is the map that holds the latest value per key. And we also need a vector called deleted keys, which essentially keeps track of keys that were deleted kind of between snapshots. So we do it like this, and I will derive these implementations for KV snapshots. So one thing we need to do now is to import the OmniPaxos snapshot trait and then implement it for KV snapshot. So we will write implement snapshots of KV commands for KV snapshots. So this will essentially give us an interface to implement how to create a KV snapshot based on a sequence of KV commands from the log. So we have this first function use snapshots, which we will simply put it through. And then this create is, as I said, how to create a snapshot from a sequence of entries. So in our case, we want to first have these 2 fields, snapshotted and deleted keys, that are empty. So an empty hash map and an empty vector. And then we want to iterate through every entry and then apply the change to the snapshotted hash map, right? So we will match on E. And here we have 3 kinds of commands, right? We have puts, which holds a key value struct, it's the key and the value. And here we will just insert it into our snapshotted map. And with deletes, as I mentioned, they are slightly trickier because we might get a key that we try to delete, which was part of the previous snapshot, but not the current one, right? So we created this key in the previous snapshot and we don't have it in this current one. So first of all, we will try to at least delete it from our current hash map. But the problem is if it doesn't exist in this current map. So then it will return none. And in this case, we have to insert it into the deleted keys so that we keep track of a key that was not part of this snapshot, but got deleted, right? And then the get we can ignore since we don't put gets in the log. So now here we need to just call retain so that we only keep those keys that were not in the snapshot. this. And then finally here, we just create the KV snapshot based on this snapshotted and the deleted keys. Here, and I think this push needs to be closed. Yeah. And now, so this is how we create a snapshot. And next up is how we merge the current snapshot with a newer snapshot, the diffs of a newer snapshot. So for that, we will iterate through the key value pairs in the more updated, or the diffs from the more updated snapshot, which is like this. And then we simply insert it into our snapshot like this. And then now is the case where we need to handle those keys that were deleted in this newer snapshot, but they didn't have that key. So we need to remove it from our current snapshot. So we can simply call remove of the key here. And then just for sanity, we can clear the snapshot or the deleted keys here. Okay. So another thing we need to change here now is that if you remember earlier, we derived this entry for KV command. And this is simply because we didn't want to use snapshot in the beginning. But now that we want to use snapshot, we will remove it here. And instead, we will implement entry manually. Like this. And this entry, we need to import the entry from OmniPaxos storage. And now we can implement the members, which is simply what is the type of our snapshot. And in this case, it's our KV snapshot. So now we have defined essentially how to create a snapshot from KV commands and how to merge a current snapshot with a newer diffs of a newer snapshot. And we will now add in the server when to actually draw the snapshot, right? So in this case, we can, for example, create a snapshot for every 5 entries. So here we can do it like this. And when we want to create a snapshot, we simply call OmniPaxos.snapshot. And here we need to give it some index. And in our case, we will give it the log index to draw the snapshot. If we put this as a none, then it will simply, OmniPaxos will simply try to draw the snapshot at the furthest point in the log, which is the decided index. And then the second argument is whether this snapshot should be performed only on this server or forwarded to all servers so that they all draw the snapshot. But here in this case, every server will do the same check and perform the same function and do the same check. So we can just put it to local. Yes, and for the sake of the demo, we can also print how the log looks like before the snapshot and after the snapshot, right? So here again, we will use the self.omnipaxos read decided suffix 0. And then here we do the log after. So now let's try out the snapshotting feature. And as usual, we will create or start our system using Docker Compose. And then here I will attach to the client. And at the bottom, I will attach 2 servers. And so the idea here is that when we successfully do 5 operations, we will see that our log should get, so it should squash these 5 entries into a single entry, right? So now we had 5 puts, and we squashed them into one snapshotted entry, right, with the latest value per key, right? While before we had 5 separate entries, right? And we can now do 5 more to see what happens. We can do delete. We can add more values. Yeah. So now we see that before the snapshot was taken, we had first of all the snapshotted entry up to here. And then we also had 5 entries after that, right? And what happened with the snapshot is that we would squash these 5 entries into one and then merge it with the preceding snapshot, right? And here now, after snapshotting, we see that we only have 1 entry left. And we see that it's the latest value per key, and also we deleted A, so A is not part of the snapshot anymore. So this is how snapshots work in OmniPaxos, where we squash multiple entries into one to prevent the log from growing infinitely large. So this concludes the tutorial. And to summarize, we began with a single server setup that was not fault tolerant. And we made it fault tolerant by introducing more servers that replicated the database using OmniPaxos. And the API of OmniPaxos meant that we only had to implement how to interact with the replicated changelog and how to perform the messaging between different servers. We didn't have to worry about implementing replication or consensus safely ourselves. And thank you for showing interest. And if you want to learn more about our library, please visit our website, omnipaxos.com, for more examples of other features, such as flexible quorums that I hope to share in upcoming tutorials as well. So please stay tuned for that.